Okay, it looks like we are good to go. I'm just going to go ahead and get started now. That's that. Alright, hello everyone and welcome to our new series here. This is going to be a smaller project, but it's going to be a fun project nonetheless. And we're going to be actually implementing something called Conway's Game of Life. So we'll first be implementing the engine or the actual algorithm behind the game, and then we will be displaying that in the console, so we get the results in the console to make sure everything works. And then we will also be looking at how to implement this in a GUI, so with OpenGL. So we'll be doing that in C++. So first of all, what is Conway's Game of Life? Well, essentially what it is it's not really a game, it's a zero-player game, because you can't really, there's no user input after the initial state. So when the user inputs a state, that's what it goes off of, and there's nothing else. So this is an example here of an initial state. So you'll have an initial state and it will evolve based on that state. So every iteration or every evolution will actually be that will be that what we iterate through. So this, hold on, let me just make sure this is going through. Okay. Yes, we're good. Okay, so yeah, this is one example of that, where we have, this is called Gosper's glider gun, so you see how it kind of shoots little things here. But how do we determine what that is, and also how do we represent that? Well, essentially there are three main rules. We're going to call each one of these little blocks here cells. So if I can zoom in a little bit here, this isn't good, but each one of these boxes is a cell, and you can kind of represent this as, or think about this as like a living organism. So when we look at the rules here, in each evolution, we will go through each cell and we will test these conditions. So any live cell, meaning any cell that is highlighted here that has the yellow box, any live cell that has 2 or 3 neighbors will live. So it will survive on to the next generation. Any dead cell with 3 live neighbors becomes a live cell. So, for example, this cell right here that I'm pointing to, this would become a live cell because there's 1, 2, and 3. And when I say neighbors, I just mean the surrounding 8 blocks. So this box right here, these are all neighbors to this cell right here. And then the third rule is any all other live cells in the next gen, or all other live cells will die, and then all other dead cells stay dead. So what happens is, we can break this down into 2 rules. So a live cell that has more than 3 neighbors will die if, say, by overpopulation, as it says right here. And then on the other hand, we have live cells that have less than 2 live neighbors die, so by underpopulation. So, for example, this cell right here would stay alive because it has 2 neighbors. But then we see this cell right here only has 1 live neighbor, so it will die in the next generation. So if I start this, what we'll see is that we will go through the evolutions. So like that, and you see how it iterates over and over again, and then they actually just died out. And a lot of the interest in this game, or I'm gonna say quote unquote game, is that you can't really predict it. So everything is completely random. So you can do whatever initial state. You can sometimes get patterns like these. These are oscillatory things, but they're moving, and there's these patterns like here. So still lifes, these are patterns that will stay the same. Oscillators will stay in the same spot, but they will oscillate between states. And then spaceships, I was actually mistaken, these are spaceships, but and spaceships will essentially move in one constant direction. However, these are somewhat oscillatory too, because they return to the same shape every time. They're just moving location. So yeah, you'll see that. We'll see how a few of these work when we display this in the console. All right, so let's go into our code here, or into Visual Studio Code, and we'll start just by creating our main file. And we can go ahead and include stdio.h, and then we'll just do our hello world just to make sure this all works properly. And then we will also create our header and source files, so conway.h and conway.c. So conway.h will have nothing in it right now, and then conway.c will include conway.h. And then if I go into the console here, and I'll just do my debug, or run, sorry. I have the run scripts in here. It's just your typical GCC run commands. And so it'll say hello world, which is exactly what we want. All right. Okay, so that's good. And now let's start by looking in conway.h, and we're going to see what methods we need. So there's going to be one utility method that we'll need, which is just our modulo. So int mod, which takes an integer n and an integer d. Now the reason why I have this function is because we're going to define our game board as something that you can wrap around in. So we're not going to have this ever expandable region that you'll see over here that you can scroll on forever and ever and ever. So we'll have a finite region, but it wraps around, so kind of like Pac-Man, where if stuff goes above the top region, it'll come in the bottom border, left goes to right, and so on and so forth. So I can just stop that there. So the modulo there, that's going to be a utility method, and the reason why we need this extra method and we can't just use the modulo operator is because negative numbers, I found that they don't work too well with the modulo for some reason, but so we'll be fixing that here. And then we'll have our structure to represent the actual game itself, so type def struct, and we'll call this Conway. Now in here, we're going to have the dimensions of the board, so integer x, integer y. We're going to have a flag to tell us whether or not we want to wrap, so character wrap, and that's just Boolean 1 or 0. And then the way to actually represent the board, well, we're going to be doing that using characters, and we could do a 2D array, but because these are variables and we don't know exactly what their value is, we can't set up a 2D array in the structure. We could do double pointers, but that would be a lot of allocation and deallocation. So what I'm going to do is just have a single string, so character pointer board. And then what we will do is we'll have a function that maps us, or that gets the value of a cell using a 2D coordinate. So we'll have some function to map a 2D coordinate to a 1D index in this string here. So it'll essentially just be sequentially putting in rows in this string. And then we can actually just write that function real quick. This is the integer, return type integer, and it Conway cell. And this will pass in a Conway pointer C, so the structure that has the board and the dimensions, an integer x and an integer y. So we'll copy this definition and we'll write it right now just to show you guys what I'm actually talking about with it. So once again, the only time when we would want to wrap around is if that state is true. So if c.wrap, then we're going to want to take the modulo. So x is equal to modulo of x and c.x, and then y is equal to mod x and c dot y with c dot y. So we're essentially just getting this x and y to be within the bounds of x and y here. So when we're testing our neighbors, what's going to happen is, say in this little, if this is our upper bound, if this is y is equal to 0, then we're going to be testing y is equal to -1 above. Or if this was on the bottom, like so, we'd be testing whatever the number of rows is. So we'd want to wrap that around so that we take these neighbors up here instead of looking into nothing. Only if we're wrapping though. So if wrapping, then reduce. Otherwise, we're just going to need to check the bounds. So if x is less than 0 or x is greater than or equal to c dot x, or y is less than 0 or y is greater than or equal to c dot y, then just return 0. I put an extra parenthesis in there. So if we're not within the bounds of 0 to c dot x non-inclusive, then just return a 0 because it's like there's nothing there. And then after this, we can just return the board, or return the index, so return c dot board. And now the index mapping will just be x times c dot y plus y. So x will be, so we're essentially having our rows have a size of c dot y. And I'm kind of having it backwards here with an xy plane, but it's okay. So we have x as the number of rows, and y as the number of columns. So c dot y is the width, and then c dot x is the height. So to go down x rows, we need to multiply by c dot y, and then we add y to get the column index there. So that's just a simple mapping, linear mapping to get the string index. All right, so that's the Conway cell, and then I guess I can just quickly do the modulo function here, which just returns an integer. I pass an integer n and integer d, and while n is negative, we just want to add d to it. So while n is less than 0, n plus equals d, and then we just are going to say return n modulo d. And this does not change the result, because if we add multiples of d to n, then the remainder of a division of n with d is going to stay the same. Like for example, if we had a -5, or let's say I'll use a positive example first. So if we had say 5 and we wanted to reduce it by 6, so our result would just be 5 modulo 6 is just 5. But if we added 6 to 5, we would get 11, and 11 modulo 6 is still 5. So that property is maintained if we add multiples of d, of the divisor. All right, so those are the first two simple functions. Now we can actually start writing the functions that will allow us to simulate the generations. So we'll have void Conway init, and we're going to pass in Conway pointer c, so a structure to write to, a character wrap as the state, and then integer x and integer y is the width and height of our board. Then we're going to have a void Conway seed, so this is kind of our initial seed. This will just be the initial state, so you can pass this in to a structure pointer, pass in the character pointer seed, and then we're also going to have a character representing the empty value. Because we cannot type in like a \0, or that would be either super inconvenient, we can just have a parameter to denote what a dead cell would be represented by in the seed, and it will often just be a space. And then we'll also have the ability Conway seed using a table, so we'll pass in a Conway pointer c, and then a double pointer seed, so a pointer to string, or an array of strings rather, and then once again the empty character. So those are the initialization ones. Then we're gonna have our simulation. So void Conway simulates, pass in a pointer to a Conway, and then it's just that's the only parameter. And notice here how that, like I just said, that's the only parameter. There's no other input that we need because it's completely reliant on itself for the input. It takes its previous state as the input to the current simulation. And then we'll have an ability to simulate multiple, so simulate n, pass in the Conway pointer c and an integer n, and you'll see that simulate n will call simulate a certain number of times. You might expect, well, in some algorithms, well, maybe you could make this more efficient by doing multiple calls at once, or you can kind of predict where it will go. Well, like I said, with Conway, you can't predict where this is going to go. There's no way to know, okay, from this, without doing it by hand or in a simulation, you can't predict where this is going to go. You see that you'll have steady states here with the blocks, but you can't predict where this is all going to go. It's quite interesting. All right, so there's that. And then void Conway destroy, which will just be our destructor passing a Conway pointer C. All right, so let's copy these signatures over. I don't even want to know what that says, Yash people. And this is not. I'm not going to guess that. If you could provide a translation, that'd be good. Okay. All right, so for our constructor, as we have seen before, it's just going to be initializing our value. Bing chill. Okay, good. I was thinking something along those lines, but I am not going to take the social credit test with John Cena here. Okay, so first quick check is if not C, then return. There's nothing to check. There's nothing to initialize because this pointer is invalid. And then we'll do a little check for the bounds here just to make sure that X and Y are positive. So those are just our two quick checks. And then now we'll just set the values up. So c.wrap is equal to wrap. c.x is equal to x. c.y is equal to y. And then we need to allocate our string here. So c.board is equal to malloc x times y, because in a table, a 2D table, when you have x rows and y columns, you're going to have x times y cells. So that's why we're allocating a string of that length. And you'll see here how x rows and y columns, we're just going to be putting in each row, we'll be putting in one row, and then the next row will be the next y characters in this linear string here. And then we just want to set our characters to 0, so c.board 0, and then x times y for the number of characters. And then we actually need to do a few includes here that I forgot. Include standard io.h. We'll need that for printing. And then include standard lib.h for malloc, and then include string.h for memset. So malloc once again is stdlib, and then memset is string. These are usually the three includes that we'll have in most C files. Bacon or burger, hello. Okay, and then for Conway seed, this is going to be a little more complex than you might think. If we pass in a string, then why not just copy it over using memcopy? The only difference is we have this extra parameter of empty in here, so we need to iterate through each character and replace the characters that are the empty with the 0, because in our in our board string here, we're going to be representing empty or dead cells with just the value 0. The character value 0, which would be the terminator character. And we'll be representing live cells with a 1. So we need to test each character to determine what to use. So we'll say for integer I is equal to 0, I is less than c dot x. I can actually just have another value, n is equal to c dot x times c dot y, and then I is less than n, I plus plus, and you'll notice here that n is just x times y, which is our string length as we allocated. So we're going to say c dot board at I is equal to, so we're just going to test the character c dot I, and if that's true, or c dot I does not equal empty, and if that's true, then we put a 1 for a live cell and a 0 for a dead cell. And then, so that's that. Linear, that's a one-dimensional string, and if we're passing in a table, which will be more common, then it's going to be pretty much the same thing. We're just going to be keeping a counter up top, so integer I is equal to 0, and then for integer x is equal to 0, x is less than c dot x and x plus plus. So when we pass in a double pointer here for a string, we're passing in a list of strings. So we have x strings, and each or c dot x, that's the number of strings, and then each string has c dot y characters. So for integer y is equal to 0, y is less than c dot y, y plus plus. And then for each character, we're once again going to test it. So c dot board at I is equal to seed at x at y does not equal empty, question mark 1 0. So the reason why I can use an index here is, well, just because, well, I'm going to actually have to increment this y plus plus. So this will just count us through the characters in the 1D string, but we're getting the character in the specific cell in our input table. And then we're once again doing the same test. What you could notice is that I could easily replace this I with an x times c dot y plus y, and that would perfectly match what we had up top for getting the index in the Conway cell method. So I could easily replace that, but since we're just counting up, we don't want to do that expensive calculation every time, so we're just going to increment a counter. I think I might need to disable chat. This is not good. This is getting too, I'm disappointed in this community right now. Okay. Now for simulate, this is going to be our big method, so I'll leave that for later on. Simulate n, we'll just call simulate n times, so while n minus minus, we'll say Conway simulate c, so we'll just use this structure n times and simulate it. I don't want to assume that that was propaganda either, but if I were to make an educated guess, it would probably be John Cena's being chilling video. And then I also actually forgot an extra method, but we don't need it actually. Okay, for destroy, destroy will just actually clear all this stuff. So if c and c dot board we're just going to reset our dimensions to 0 and then free the board. So what will happen is in our main method, we will create we'll have just not a non-pointer, a primitive structure variable, and then we'll just pass a reference of that into each of these methods, so that we don't have to worry about freeing the actual pointer variable here. We will leave that to the caller of this method, who actually manages the memory. So that's destroy. Now for the simulation. So this one is, it's not going to look like a lot, but there's a little bit of methodology that has to go into this. So we're first going to start with a little, we're going to start by doing one way, and then I'm going to talk about how that's wrong, because I did this. So as we did with seed using a table, we're going to have a counter. So integer I is equal to 0. Then for integer x is equal to 0, x is less than c dot x, x plus plus. And we're actually going to iterate row by row. I'm not going to disable comments. This is entertaining. So we'll iterate through each row, x going from 0 to c dot x, and then integer y is equal to 0, y is less than c dot y. So that's each row. And then we're first going to count the number of active neighbors. So that's why we're iterating this through this using our actual cell coordinates here, so the 2D coordinates instead of just the string index, because it's easier to find our neighbor indices just by counting or just by going like at it this way. So we'll have a counter here, integer active neighbors is equal to 0, and for integer xi is equal to -1, because we're going to be centered around, so if I can zoom in, oh, that's a lot. So if we were looking at this cell right here, and we wanted to count the active neighbors, we're going to start by just doing an offset of -1, -1. So if this is our active neighbor, or if this is our target cell, we'll start by with -1, -1, which is this cell right here. That's the cell with an offset x coordinate of -1 and an offset y coordinate of -1. So xi is equal to -1, xi is less than or equal to 1, xi plus plus, and then the same thing for the y. And then we're just going to determine if this value is actually active. So the if statement here is if xi or yi in parentheses, because we don't want to count the current value, because this is just offset 0, 0 with respect to our target cell. So we don't want to count if this one's active. We only want to talk about the neighboring cells. So if xi or yi is not equal to 0, and Conway cell, so we're going to call that function, passing in c, and then do x plus xi and y plus yi. And so this is just where we're applying the offsets. So if that value is active, or if Conway cell returns a non-zero value, then the neighbor is active. So active neighbors plus plus. Okay, and then what we're going to do now is we're going to essentially go through these three rules that we have, which were up here. Those three rules. And then we're going to compare them or apply those rules with the active neighbors count that we have. So the first condition is going to be a live cells, or I'll just say live cells with 2 or 3 neighbors stay alive. So what's that condition going to be? So we need to make sure that the cell is live, and then the number of neighbors has to be 2 or 3. So if c.board at idx, so remember we have this parallel counter here, it's I not idx. So that's the character representing the current cell in the 1D coordinate. And then we need to do an AND with, now in parentheses, active neighbors is equal to 2 or active neighbors is equal to 3. So this condition has to be met here, 2 or 3, and then the current cell also has to be active. Oh, is that the translation? All right, thank you. Thank you, Yash. Appreciate that. So if we have this here, so if the live cells with 2 or 3 neighbors, if the cell is live and it has 2 or 3 neighbors that are live, then we stay alive. So we'll say c.board at I is equal to 1. That's just a formality, but we'll do that. And then else if, now the second condition is dead cells with 3 neighbors become live. So the condition here is that we have to have a dead cell, so c.board at I needs to be 0, and then active neighbors needs to be 3. So else if not c.board at I and active neighbors is equal to 3. And the reaction here will just be c.board at I is equal to 1. This lore is going so deep. Was Fast and Furious actually filmed in Thailand? Well, fuck. Yeah, that definitely is propaganda. I don't know what John Cena's talking about. He apologized for mentioning Thailand as a real company or a real country, but like, okay, yeah. But that definitely is propaganda. And then the last condition here, else, is just that all the other cells remain dead. So there's no condition there, it's just everything else goes to dead. So c.board at I is equal to 0. So this could be our thing, and then after we do this if statement, we need to say I++ to move the cursor up. The only problem with this is, some of you might be able to figure it out, but when we set c.board at I to 1, if we're changing the value, then this actually will affect our active neighbors counting for the cells that have the current target cell as a neighbor. So what we're going to have to do is create a temporary string here at the beginning. Character pointer temp is equal to malloc c.x times c.y, so it's the same size as the initial one. And then what we're going to do is every time we set c.board here, we're just going to say the temporary string at I is equal to 1 or 0. So temp at I is equal to 1, temp at I is equal to 1, and then temp at I is equal to 0. And then now that we have the new data representing the next generation in a temporary string, we just need to copy that over. So mem copy, the destination is going to be c.board, source will be temp, and then the number of characters will be c.x times c.y. And then we just free temporary. So the biggest thing there is just making sure that you're writing to a temporary string, because then you'll be counting the next generation as when you're considering the active neighbors for the current generation, which is not what you want. And that's pretty much the whole algorithm. It's a very simple game. even though it's not really a game, but it's still extremely simple. Now, next what we're going to do is we're going to actually try and output this to the console. So we're going to create a helper method that outputs this to a table. So we have two input methods that you can seed with either a linear string or a 2D table of characters, which is just a list of strings essentially. If we wanted to do two equivalent output methods, you can just get the linear string by saying c.board. But we're going to have a formatting method that will actually format this into proper strings with terminator characters in a 2D table. So we're going to have another method at the end here that will return a double character pointer. We pre-allocate it here, but we're not going to copy over. I mean, you could copy over the values, but it wouldn't do anything for you. It would just be an unnecessary step because we're setting each of the characters to some value. Like, it's not like we're going to leave some of the cells unset if we don't need to. It's just we're setting all of them like that. So this will be Conway print that returns a double character pointer, and you take in a Conway pointer C. And then here we're going to have it's going to be a 2D, or it's going to be a list of strings. So we're going to have the return variable ret is a double pointer is equal to malloc c.x times the size of a character pointer, because here we're allocating an array of pointers, and we're doing c.x because that's the number of rows. And then for integer x is equal to 0, x is less than c.x, x plus plus. I'm actually going to have a few extra parameters in here. Character alive and character dead, to indicate what to output as alive and dead. Hello from Pakistan. God damn. That's pretty cool. So for each row, we're going to allocate a string in the list. So ret at x is equal to malloc c.y, because we have y characters now, times the size of a character. And we're going to do a +1 because we'll need a terminator character at the end. And we're just going to iterate through each character. So for integer y is equal to 0, y is less than c.y, y plus plus. And then we can also, similar to the input of a table, we can have an external parallel counter here. So I is equal to 0. And then in each iteration of the inner loop, we're just going to say I plus plus. And we can use this as our index into the string from the Conway structure. So ret at x, so the x string at y character is equal to c.board at I. And then if this is alive, then we're going to pass in the live character as what to set the output to, and then dead otherwise. And then after we go through the row, we want to set the terminator character so it's easier to print. So ret at x at c.y, because that's going to be the last character, is equal to a \0. And then after the outer loop, we're going to return ret. Feet pictures. Do you have those in Pakistan? I mean, I'd be willing for a fair price. Okay, so that's that is the output method, and now we can actually go into our main method and start writing the code for this. So I actually forgot to update the function definition for print. Hidiomo, that was a little bit of out of pocket, I'm not gonna lie. You might want to keep, this is extremely unprofessional if you, if this was a less professional context, as in like in an actual business, then go for it, but right now I want to keep my professionalism, so I will not be sending feed pics in the chat. How much? Yeah. Once again, it all depends on the price. Alright, let's go to main.c. And we have our hello world. We're going to define our constants here using macros, just so we can allocate our seed array. So define x as 30 and define y as 100. And then we're going to do our structure, so Conway C, and then we're going to initialize it. So Conway init, using a reference to C, 1 and then x, y. So the 1 is wrap, so that stuff will actually wrap around. I actually did not include Conway.h there. And then we're going to need two more includes actually. So we'll do include standard lib.h, because we'll need to free a string, because when we print out the return table here, we're actually going to be allocating. But I guess what we could do is just pass in an output. It would be a little simpler. Yeah, let's just do that. So character double pointer out and assume it's already allocated. So have this return void. And then instead of allocating every time, we're just going to be, you know what? No, we'll leave it like this for now. Maybe I'll change it later on. But for now, I'm just going to leave it like that. So we'll return the table that's allocated. But in main.c, we're going to need to include standard lib so that we can free the allocated string every generation. And then we're also going to include windows.h. Or, you know, we could do is just have a character double pointer. Why not make the x and y? I tried that. I mean, I think it, yeah, that works. It's just when we get to the so x, yeah, we could do constants. It's just I was running into problems with that in the array definitions, so I'll try this now, but hopefully it works. So we'll do the constants there. Macro, yeah, that is true. I do it. That is fair. But for Conway.c, we'll look at the Conway print, and you can pass in a return. So this will just be a double pointer. And then if not ret, then we will allocate. So ret is equal to malloc, and then we'll still return ret afterwards, so that if this is like the first generation, then we want to allocate it, but otherwise we just want to but if it's like the first time, then we can just pass in a null here and we'll get a string back from it. So we'll do constants int there for the dimensions, pass those in for the board dimensions, and then we're going to do our seed. So I have in the repository examples. This was one example, and this is the glider gun actually, which is cool. So I'm gonna copy this over. Yeah, I don't know why this expression must have a constant value. It's weird, but I don't know why that's doing that, because I mean, I guess I can just try and run it just to see if that works, but I don't know why that wasn't working, or why it's giving me an error. So yeah, this is one example of a Conway game. It just starts like this, and it will essentially, these two things will go back and forth, and they will, so these two little bodies here will go back and forth between these two blocks, and they'll shoot things that will go down here. We actually saw this. It's this thing. Except when you wrap around, these little spaceships here, the gliders will come back around and they will destroy the gun, which is pretty cool. Alright, so we have the seed there. And then we will call the seed method, so Conway seed table. Pass in a reference to C. The seed will be seed, and then empty will just be the space character. So all of these empty characters are just spaces, but that's what we will represent it as. This won't work with the index. I'll try it, and then if not, I'll just use macros, or I'll just I'll hard code the values in, which sucks, but I'll do it. Alright, so that's seeding the table. And then now we're going to do this simulation. So integer number of rounds is equal to 80. We'll do that to start. And then we're going to print out an integer for no, we don't have to, but we're going to print out the Conway. But how do we do that? Well, we're going to have to use the method of Conway print. However, we need to do that a little trickily, or not trickily, but we need to be careful here. So we're first going to have our character double pointer output is equal to Conway print, passing in a reference to C. Yeah, I'll try and figure out what happens here. So we'll pass in C. The live character will just be a 0. The dead character will be a space, and then I forgot to have the extra parameter there on the print method in the header file. So then we'll also just pass in null there because we want to actually allocate the value. And then what we're going to do now is we're going to pass this double pointer into another function that just prints out a table here. So we'll just do for integer, or this should be, so this will just print out a table of strings, so integer, or we can just do for integer I is equal to 0, I is less than n, I plus plus. And we'll just print out the string. So printf %s \n, and we can use this as a string because in the print function we actually give it a terminator character there. Oh, one more thing, I forgot. In the print function we need to say if not ret, then allocate each row. But I'll have just character here. So character allocate is equal to 0. So this allocate here will just be a boolean essentially. So if we would need to allocate, then we will allocate in each row. But if we already have a pre-allocated string, then we don't want to. I have no clue what that is, and I'm not going to try. I have actually not heard of anonymous enums before. I know what an enum is, but I don't know what an anonymous enum is. But if we want to allocate, then we'll allocate each row. Otherwise, we're just going to be allocating new memory on an already allocated table, but the previous pointer will be lost, and that's going to be a memory leak. So we'll print out the string, which has a terminator character, and the string will just be str@I. And then, or this should be table@I, sorry. And then we will just printf 2 new lines, like so. So that's just a quick print function. And then the output there. So that's we'll print out the initial state. And then the reason why I included Windows is so that we could call, or sorry, another reason why we included stdio is that so we could call clear screen. So system CLS, and this will just clear the console screen. It's something similar in, it's somewhat similar in Linux. Okay. So it's just an enum without a title. All right. Maybe I'll try that out. And then for each iteration, we're going to say while nr minus minus. Then we'll simulate. So Conway simulate, passing in reference to C. This we'll just call one simulation, and then at the end of each one, we want to print it out actually. So output is equal to Conway print, passing in a reference to C. Live is a 0 character, or is just the 0, and then space for dead, and then the return is ret, or is output, and then we need to call print table using the output. We actually forgot to do that over here as well, and the number of strings in that will just be conway.x or c.x, sorry, because there are x rows. And then we can call system CLS, and then our last include that we did was windows.h, and the reason why I wanted to do that was so we could have the sleep function. So after each iteration, we're going to want to just leave it on the screen for a little bit, and we can just call sleep 50 milliseconds, so that it'll go. Is system bundled into standard lib? I'm not sure. It is. My mistake. Yeah. It's not stdio. My mistake. Yeah. Yeah, so system's in stdio, or is in standard lib. Right, and then after all the iterations, we're going to say Conway destroy, pass in a reference to C, and then we also have to deallocate our string here, but we have to do that before destroying Conway because we need the counter. So for integer x is equal to 0, x is less than c.x, x plus plus, and this will just be free Conway at, or sorry, not Conway, output at x, and then we want a free output. So everything that we allocated in Conway print in that first call, we're just gonna free. So each of the rows individually, and then we free the whole list at the end. Okay, so that is that, and let's try and run this now. I'm just gonna run and see if it works. Nope. Aha! What happened? Okay, so I think I do need to. I don't know why that, because it should work. Or it's weird that I need to have this as a macro because constants should work. I don't know why. So I'll do x as define x as 30 in a macro, and then define y as 100 in another macro. Okay, now let's. This is going by very fast, and we also can't see everything. So let me zoom out a little bit, and you can probably see this a little better. Yeah, this will be better. Here we go. That's not right though. Let me reduce the number of iterations so I can see the initial state real quick. Just do a 0. but I won't call CLS. Okay, that's right. Let me do one iteration. That's not right. Okay. Yeah, that is just not right at all. Alright, I guess we'll have to go into our function here and see what's going on. I think the input and output methods are good. The input method is definitely good because it read it properly. Alright, so here in simulate we allocate our temporary string, x times y. I starts at 0, then we go x goes from 0 to c.x, y goes from 0 to c.y, y plus plus. Counting our neighbors, xi goes from -1 to 1, increment y -1 to 1, increment, and if xi or yi, so these at least one has to be non-zero, so we're not the target. And with a Conway cell, alright. Let me do a little bit of debugging here just to see if Conway cell actually gives us the right thing. So let's see, it's 0, 1, 2. So 13. So x is equal to 13 here. 0. So 13.8 should return a valid, should return 1. So we'll do debug. And then after seeding, so we'll say break 61. Print Conway one. Okay. All right. Okay. I think Conway cell seems to be working. So active neighbors plus plus. Okay. So c.board at I is equal, if that is a non-zero value, and active neighbors is equal to 2 or 3. Good. Temporary and I is equal to 1. Else if not, cboard and... So these conditions are correct. And then I++ afterwards, isn't it? Oh wait, is that? No, that's correct. 30 strings and each string has 100 characters. Yeah, that's right. Yeah, so that's our initial state. Good. So we simulate output. Okay, that's just not right. Because these are dying when they should be the blocks on the end should be a steady state thing. Okay. So it's not counting it properly. Conway cell takes the modulo. Is it modulo that's not working properly? While n is less than 0. No, that's right. X times c dot y plus y. This is not making... God damn it. X and y are within the bounds of 0 and c dot x and c dot y. We've ensured that with the modulo, so we reduce it. We're either reducing it if we want to wrap, or we just hard check the bounds in this condition here. X times c dot y plus y. Is it the indexing that's not right? Or no, the printing worked because the initial state is fine. It has to be the simulation because it's printing properly. Give me 2 seconds. I'm going to try and copy something from my GitHub. Alright. Is that right? Hold on. This could be something. I don't know what I did differently. Let me do like 80 rounds. Okay, that's right. What? God damn it. Okay, well, what you'll see is that... Here, let me do more rounds. Let me do... That was 80 rounds, really? Let me do 800. That's something interesting. So you'll see that this little glider gun is tracking down and it wraps up top. It's going over here. We have multiple of them. I'm sorry, I should put an epilepsy warning. This is not good. This is not good. But essentially we're continuing to wrap around, still wrapping around. And you see that it will come over in the corner here. So this corner wraps over here and it's going to start interfering with the actual gun itself. So it won't give off gliders as it does usually. I'm not sure if VS Code has that. Maybe I can check that though, because that sounds interesting actually. Okay. I don't know what I did differently. I copied my code from that I had already, so let me do a little \z. Alright, temporary. Temporary is x times y. I is equal to 0. X is equal to 0. X is less than c dot x. Yeah, it's pretty interesting. We'll just wait until we put it in our using OpenGL and put it in our window. It'll be even cooler. We don't have to have the glitching stuff with the CLS calls. I mean, I can also slow it down a little bit. Sleep every 100 milliseconds. But I'm just trying to. All right, what changed? I++. 110. Okay, I don't honestly have zero clue what changed. But we're gonna try this again. And yes, it's going slower now. But you'll see that this glider gun here, it's shooting stuff off, and these will wrap around. So they'll start here and they'll wrap up to the top, and you'll see that they keep going down this diagonal until they reach the corner in this the bottom corner here, and they'll go to the upper left, and then they will actually destroy the gun, which is pretty cool. But what's also interesting is that these little blocks here, the 2 blocks, so yeah, you see this coming down now. It's going to start interacting with this gun itself, and it's going to destroy a few things. So that block stays there, and it's unpredictable, which is the really cool part about this. But it's been used to, or you can see it having correlation with bacterial growth, stuff like that, and so it's really awesome, actually. I'm just gonna still try and figure out what I did wrong. Okay. Is it simply just changing I to IDX? Because that should not be the change. I swear, if that's the change, there's no reason for that to be the change. Okay, that wasn't changed. So it's something in the active neighbors check, maybe? Oh, you... I just found it. Okay. This condition, y is less than or equal to 1, not less than. It has to go from -1 to 1 with the bounds. So when we're checking active neighbors, we need to have these bounds as inclusive. Okay, so now let's run this again. Oh, it's still going. And yeah, so that's that. It's really cool. It's awesome. So yeah, you can play around with this. There's a lot of really cool things that you can find online. I mean, there's this simulation that we had right here, but there's also, I forget where it was, but there was, maybe it was this thing, but there was a site that had a bunch of examples on here that was really cool. But you can just see all the patterns that people did not create that, but yeah, it's all stems from these 3 to 4 rules, depending on how you look at it. But it's really interesting how this stuff can model real life situations, specifically with bacteria stuff. So yeah, stuff like that. And there are a bunch of the tests that you can see in here that you can kind of test to make sure that your algorithm is working, so that you can see that the spaceships will oscillate, or that will move and oscillate. These oscillators will oscillate, and then also the steady state ones will just stay still, which is really cool. And yeah, so that's pretty much the first part of this. Next time we'll be looking at creating our OpenGL project. I'm letting you guys know now, it's gonna be a while, just because I'm going home for the holidays. So I won't be here for 2 weeks or so, probably early January, but I will definitely be working on the code at home. So I'll have stuff to stream or do a video on when I get back. But yeah, that's pretty much all I have for you guys today. Hope you guys enjoyed and maybe learned something. And yeah, I will see you guys in a few weeks. Have a good one.